Excellent. So, good afternoon and welcome back. Let's get started really quickly with Geoffrey's lecture, second lecture on DG methods.
Okay, welcome back, everybody. Before I get back to talking about DG, since I'm going to once again use the scalar wave equation as an example, I wanted to say a little bit more about why that example is so applicable when you're talking about numerical relativity. And the reason turns out to be that you can write the equations of general relativity in a certain formulation, the generalized harmonic formulation, so that it actually is very similar, at least the principal part, the part with the derivatives that describes how the equations work is very similar. So let me start out by coming back to the scalar wave. So I'm going to write scalar wave system right here. And when we reduced it to first order, we did it yesterday or the day before and again. Harold did it this morning. It's a system where one equation is partial TG plus capital pi is equal to 0. And then partial T pi plus partial K pi K is equal to 0. And then there's three equations, partial T pi I plus partial I pi, and that's equal to 0. And how are these pi's and phi's defined? Well, pi, you have it right here, minus pi is just the time derivative of the wave amplitude g, and then there's the constraint that defines phi, and the constraint is the partial derivative of g minus phi I is equal to 0, so we can call that Ci. Okay, so that's the scalar wave system. Now, I want to show you for comparison just the principal parts. So remember, the principal part of the equations only counts the terms with derivatives. We reduce them all to first order, and there's only first order derivatives. So if I do the principal part, then what that means is the principal part is everything except the source terms. And there's only one source term here. Which equation has the non-zero source term in it? First one, and the source term is just this pi. So if I get rid of that, then I'll use this notation here for the principal part. The squiggle equals means this is the principal part, only the derivative terms. And now I want to compare that, and I'll show you, I'll just write out what the principal part is for the real, for one formulation of the real equations of general relativity in vacuum. So this is generalized harmonic. The generalized harmonic formulation. There's lots of formulations that you can use in numerical relativity. I think you probably met the BSSN formulation last week. This is the formulation that we use in Spec and Spectre, and it has some nice similarities with the scalar waves. So in particular, one equation is an equation for the space-time metric GAB, and then there's a term involving partial KGAB. This is the principal part for the space-time metric. G, beta I here is the shift. I'll remind you what the lapse and shift are in a second. Partial T capital pi AB minus the shift. Wait, I don't mean B, I mean beta K because I'm summing over these. So that's a K pi AB plus the lapse. I'll remind you what that is in a minute, what all these things are. Gamma, and this is the inverse spatial metric, ki partial k phi IAB. And that is the principal part for that one that's equal to 0. And then there's an equation for phi IAB, and its time derivative minus the shift dotted into the derivative of phi IAB plus the lapse times partial I pi A B is equal to 0. Just give me 1 second here. Just need got my reading glasses for this. So, how are pi and phi defined? Well, phi is defined exactly in the same way. Phi IAB is equal to partial I GAB, just like partial IG is equal to phi I in the scalar wave case. And then for pi, you can write pi AB is equal to minus a normal vector, which I'll call n, and a partial A, and then I'll explain what this is, partial A G A B. Okay, so what is all this? So this comes back to some things you were talking about last week with the 3+1 decomposition of, oh yeah. What was that?
3 indices of A.
3 indices of A. Oh yeah. Sorry about that. That should be a C. Good catch. Thank you. Okay. So what is all this? So if you take space-time and split it up into some slices of space, so T and T plus delta T or something like that, then if you've got a point here, and now I'm going to use this n for the normal, n with a C or an A or a B, not IJK. This isn't a spatial normal. This is a normal to the spatial slice. It's not a normal vector to like a cell within the space. And in terms of that normal, then the time vector, the direction that time is flowing, is going to be equal to, these vectors are getting really small. Maybe I should have drawn that bigger, but basically that's going to be equal to the lapse times the normal vector plus something in the spatial direction, which is the shift. So the lapse and shift, lapse tells you the rate of flow of time, in a sense. It's the rate of the change normal to the spatial slice, and then the shift is the amount that things move within the spatial slice if you want this and this to have the same coordinates. So the lapse and shift are telling you something about how the coordinates are moving. And then there's within each spatial slice, there's a metric, gamma ij, and the combination of gamma, lapse, and shift turn out to just be components of the space-time metric. So when you see these lapses and shifts, those are just components of the space-time metric that happen to show up. So the reason I wanted to show you this is to sort of justify why I'm spending such a big deal looking at the scalar wave system. Just like the scalar wave system, there are equations for g, pi, and phi. Phi is the spatial derivative of g, and pi is something like a time derivative. But here, because you have to worry about, because this is space-time, here it's the derivative normal to the surface. In the flat space scalar wave, the defining pi as a time derivative is kind of equivalent because you don't have to worry about curved space-time. So here pi was just defined as minus the time derivative of g. Now, yes, these equations are messier. The b's, those non-conservative terms in the general form of the equations, those are not as simple over here as they are over here. Here, these spatial derivatives like this just have coefficients of 1. whereas here they don't. But there's enough similarity. I just wanted to show that to you to tie things back to last week a little bit. So, and also to justify why I'm saying this is a week talking about modern techniques in numerical relativity, and I'm actually mostly just talking about the wave equation. They're actually kind of related. Are there any questions about that before I get back into the discontinuous Galerkin stuff? Okay. If not, then let's get back to, a lot of times you get tired of saying discontinuous Galerkin and you just call it DG. So let's get back to talking about DG. Last time in DG, there was, where we left it was with this, we had derived the weak and the strong form of the equation. So let me write down the strong form where we left it once again. So we had 0 is equal to an integral over an element of the volume of that element, and I'm assuming that's 3D, times some basis functions, phi I, phi j breve, and phi I breve, and those basis functions depend on space, and then the stuff in the square brackets does not. So the stuff in the square brackets, then we have a time derivative. Let me remind you that repeated indices are summed over, plus a flux term, partial I f I alpha, and then there's that. And then there's the non-conservative terms. These are the B's I was just mentioning, I alpha beta, partial I beta j, minus the source terms, j breve alpha. Okay, and then there's a second thing. There's a surface integral over the boundary of the element, which I'll call partial, omega k, the boundary of the kth element, d squared x times g j breve alpha, that's the numerical flux. And in the strong form, you have ni int f int I alpha j breve plus d j breve alpha and on. Okay. Now, this term here was the numerical flux. And this term here was the non-conservative boundary correction. And then this is the time derivative, the flux of the non-conservative terms, and the source terms. So that's sort of where we left it last time. Is there some problem? Yeah. Sorry? Phi is in, oh yes. And this, because these are spectral expansions, of course you're going to need a phi j. Is that's what was missing? I'm sorry.
One comes from the spectral expansion, and the another one.
Oh yeah, and another one because I just multiplied everything by it. Yeah. Okay. Yes, that's exactly right. Thank you. Yes. Okay. So now I kind of wish I'd written this in a different order. So let me fix it because I want to put the spatial terms together. So there's a phi I that depends on space and a phi j that depends on space, and there's a surface integral d squared x. All right, is that looking better? Okay, thank you. So, yes?
These are the
Oh, the mic's not working. Okay.
so these are the in the coordinate system of the physical one, right?
That's right. The d cubed x and the d squared x, that's the physical one. I'll draw that again in just a moment. Does that answer what you asking?
Yeah, so these phi's are not orthogonal in that coordinate system, right?
Yeah, the phi's aren't even defined in those coordinates directly. The phi's are defined in the logical frame. They'll go from like, they'll be built out of polynomials going from -1 to 1. And then you would have to start with that and then go through the whole coordinate map to get back into the, if you wanted to do the integral in the physical frame. Or you could just change variables to the logical frame and just introduce a Jacobian. So you also could write these d cubed x's as d cubed size, the logical variables, but just with a Jacobian afterward, the determinant of a Jacobian.
No, but can we write the expansion that, let's say these expansions in terms of the phi's in the physical coordinates as they're not orthogonal in the...
Yeah, you're not necessarily just going to get 0 if you do this integral. That's right, because of the determinant of the Jacobian. I mean, I'm not sure.
So can you just tell the flowchart basically what are the coordinate system, and you are basically writing the expansion of every coefficient in terms of the phi's, right? You are expanding your functions in the physical space in terms of the phi's.
Yes.
And those phi's are not orthogonal to each other.
No, in general, they're not. They're not.
So can you write the expansion then?
So what's the question? Can you write the expansion without orthogonal basis functions? Yes. I don't understand why not. Yeah. Okay. Do I understand the question?
Yeah.
Yeah. Those phi's don't need to be orthogonal in the physical space. Okay. Now, if I wanted to rewrite this in the logical frame, all you would do is you would take integral d cubed x and turn that into integral d cubed logical times the determinant of some Jacobian, which would be like partial xi, partial psi I bar, something like that. And in that case, if you're going to define these in terms of polynomials defined on the unit cube, then you can sort of see that they're not necessarily orthogonal when you do the integral, because this term here isn't necessarily 1. So even if in the logical frame the phi's are orthogonal, we talked about this yesterday, this determinant means that it's not necessarily true that you're just going to get 1 when you do the integral of them in the physical frame. Because the physical frame introduces this extra Jacobian if you change the coordinates back to ones where you know how these are defined. Okay, now, yes?
Is it easier to write the expansion in the logical frame as compared to the physical?
Yeah, normally what I would do is I would define what these phi's are in the logical frame and then just use the coordinate map to send things back. So in the end, when you actually evaluate these integrals, remember the only spatial dependence is outside the square brackets in these integrals. And the way you would actually evaluate it is like this. You would go back to the logical frame, and because this derivation started in the physical frame, this integral is going to pick up this determinant. But then once you have that, now you know how to integrate everything, because now this integral is just over the unit cube where all your polynomials are defined if these phi's are based on polynomials. Does that make sense? Yeah. So in particular, we are talking about the kth element, omega k. Here it is in the logical frame where everything goes from -1 to 1. And then there's some map to get you to the physical frame from the logical frame, which might be, some deformed cube or something. And so that's the map we're talking about. Other questions? Okay. Thanks for asking about these things. These are great questions. And thank you also for the fixes when I dropped some terms on the board. So now I hope we're good. Okay. So this is sort of where we left it. Now, for today, I'm going to focus on a specific case where we're only going to deal with vacuum. Oh, is there another question?
So I was just asking, so this expansion is in logic?
Well, I mean, you can do it in either frame because there's a mapping from the logical coordinates to the physical coordinates. ultimately, if you're going to use like orthogonal polynomials defined from -1 to 1, those are naturally defined here. But you could always, instead of plugging in a psi, which goes from -1 to 1, you could always take your basis function that starts out as a polynomial in the logical frame and just take the inverse of this map and transform the xi's into the x's, and then you can think of them as functions of x. It's just they don't take the simple form anymore because you've got this map stuck inside them. So suppose, let's just make this explicit. Suppose that you had in one dimension a phi, which was the ith, we'll say Legendre polynomial, and it depends on this logical coordinate psi. Well, you can also think of this as a function of x, because there's a mapping x as a function of psi. So if you put in psi, out comes x. And then you can construct an inverse map, if that map's invertible, where you put in x and out comes xi. So if you could also write this as pi, you could think of this xi as an inverse map, and what you're really putting into the function is x. And you'll get the same thing out in the end. It's just sort of your choice, right? Like you could think of this as a function of x. It's just pi of whatever this map is of x is not just going to be like, if this was P1, you wouldn't necessarily just get X, like you would just get psi. You would get whatever this map is as well. Does that kind of make sense?
Sorry. So the thing is, we are expanding the thing in logical term, but we are still keeping the terms that involve X, right? So X is defined in physical frame. And I's are in logical, right? So why don't we use a particular frame and expand all the terms in that variables?
Yeah, it's an interesting question. So why do we have these two frames? The physical frame is there because that's what we care about in the end. That's the reference frame we want to actually solve the equations in. So there's no getting away from a frame with these deformed cubes if you want to solve something with spherical symmetry or approximate spherical symmetry, something like that. You could, if you wanted to, do everything in the physical frame. I haven't yet said it. In the main derivation, I haven't yet said what these are. I've sort of alluded to eventually they'll be built from polynomials. I'll probably get into how that works. I might get into that tomorrow in more detail. But for now, these are just functions of space. And you can think of them as functions of physical space if you want to. That's fine. And then the whole thing is just in the physical space. Now, because we like using these polynomials that are defined on some reference cube, it can be convenient to introduce a logical frame and then change variables so the integral over the physical space becomes integral. You can rewrite that in terms of an integral over the logical space, and there's just this correction that shows up. And then that's nice if you want to think of these basis functions as defined this way. But that's just a choice of convenience. You could think of basis functions, as far as this derivation is concerned, you could think of basis functions that are just defined in x. They wouldn't necessarily go from -1 to 1 because your domain is bigger than that, but you could. And for our purposes, these are just some function of space that you know, and I haven't said more than that really yet. But I guess I've been alluding to the fact that eventually in the logical frame, these will end up being these orthogonal polynomials. So thanks for asking about that. I think that.
Eventually we'll be putting that transformation that is the volumetric of PQX that you have wrote, right?
Yeah, when you actually evaluate the integral in practice in the code, that's how you do it. Yeah. Yes.
In basis information, we have both constant equations and evolution equations. So here in harmonic formulation, do we have constant equations?
Oh, great question. Are there constraints? There sure are. And I only really sort of wrote one of them. So the easiest one to write is Ci is equal to partial I GAB. Oh, and this is called the 3-index constraint because it's got an I and an A and a B now. Minus phi I A B, but there's a whole bunch of other constraints too that I'm not going to write down right now. There's a 1-index constraint, and that one's actually not so bad. I'm not going to write it, but it's like one line of algebra. It's an algebraic function of G, pi, and phi. There's also a 2-index constraint, and I think that one is IA, if I remember right. I guess I could go check. I had the paper up here, but then. Yeah, just give me a second and I'll at least find out what sort of, double check what sort of form they have. Yeah, there's this. And then there's the 3-index constraint. there's one with 4 indices. I'm just going to write dot, 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 because I don't want to write them out. And then CIJAB. And then these are all sort of, 2 or 3 lines of terms, so they're a little bit messy, but not so bad. But then there's this other constraint called the F constraint, FA, and that one fills up like a quarter of a page. It's like ridiculously many terms. It's annoying. And I think it was Mark Scheel at Caltech when they were naming all these. Most of them are named C's for constraints, but this one annoyed them, so they named it F instead. And so there's lots of constraints.
We are going to solve the evolution.
In real life, in numerical relativity, this constrained system is the system that you solve. If in spec inspector, this is the system we're solving, and all these constraints need to stay satisfied. And the initial data, for instance, would be constructed to satisfy, so that when you start out, these constraints are at least approximately satisfied. Yes. So that's a great point. And yes, I sort of glossed over the constraints, but they're there, and there are a lot of them. And this one in particular is very annoying to compute. It's very expensive if you want to calculate it, and it's just a bazillion terms. And I'm complaining about it because one of my jobs was to code this up in our new code inspector, and it just took a while to make sure everything was right. It was just a lot of terms. Thanks for asking about that. Any other questions? Yeah.
I just heard about this constraint damping. What is that?
What is constraint damping? Yeah, why not tell you about constraint damping? I actually had something prepared to tell you about that. So since you asked, and we're sort of at a good starting place, I guess. I eventually want to tell you about what this D is, but before we get there, I can say a little something about constraint damping. Now that we mentioned the constraints, I'm going to do it for the scalar wave system, and then talk about how it generalizes to a formulation like this, where your wave amplitude picks up extra tensor indices, because now it's the space-time metric and stuff like that. So let me real quick say something about what constraint damping is. The issue is, if those constraints start out exactly 0, when you do the time evolution problem using a time stepper, like Harold was telling you about this morning, it will stay 0. But what if those constraints are 10 to the minus 15? Then, if your system of equations is not properly formulated, those constraints might grow exponentially. What if your constraints, even in the scalar wave, start out at like 10 to the minus 1? As written, they would stay 10 to the minus 1. And what you would like is to reformulate your equations so that the constraints die away. So let's talk about that for a second. And let me just pull up in my notes where that is, because I wasn't planning to get there yet. Let's see here. Yeah, here we go. Okay, so that's sort of the reason why you would have to do this. So now, I'm going to show you what we do, and then I'll show you why. So the idea is, if you start with this system of equations, you are allowed to add 0 to that system of equations without changing the system. So if I just did this almost sounds trivial. If I just did this plus 0, of course that doesn't change anything, right? It's just adding 0. But now the cunning part is you say, oh, well, you know what? This constraint had better be 0. And if this constraint is 0 and this constraint is 0, because if we're solving the system we want to be solving, all these constraints vanish. So what that means is you are free to add 0 in the form of the constraints, because those constraints, as you turn up the resolution, they should converge away to 0. And to the degree that they're not 0, they're just numerical error. They're not changing the physics. So in particular, you can add some multiple of the constraints. And so what I'm going to do here is just add gamma 2 times what I defined as Ci here, this thing right here that had better be 0. Gamma 2 is a non-zero constant. So this is constraint damping. You've added a multiple of the constraints, and by adding that multiple of the constraints, you want to control the constraint growth. Now, what I'll show you is how on earth does this actually affect the constraint growth, right? So the idea is these are evolution equations for the variables we want to solve for, g, pi, and phi. We can manipulate them to come up with an evolution equation instead to come up with an evolution equation for the constraints. So we could find out if this is non-zero, how does it evolve in time? I'm going to come over here and do that. So let's start out with that phi equation, partial I, plus the gradient of pi, divergence, oh, sorry, that's not a partial I, that's a partial t. The time derivative of phi plus the gradient of pi, and now we've got a constraint damping term, gamma 2 of ci, that's supposed to be 0. Okay, so now in order to get a time derivative equation for this constraint, the constraint I is partial I g minus phi I. So what we wish we had is to get a time derivative for the constraint is instead of partial t phi I, we want partial t of the gradient of g minus phi I. So the first step towards getting there is just multiply every term in this equation by -1. And now at least we've got the minus phi I part. Now, what we're going to need to do is we're going to need to add 0 again, so we don't change this equation. And this time, I'm going to say 0 is equal to partial t, partial I of g, the other thing we want, minus partial I, partial t of g. Partial derivatives commute, so this is 0. So I can add that here without changing the physics. And in that case, what I'll get is partial t of partial ig minus this phi I, which was already there. And now I have to subtract the other term, minus partial I, partial tg. But what's partial tg? I defined it over there. Partial tg is minus pi, yes. So now, since I have minus partial I, and this is minus pi, I can just write this as minus partial I pi. Okay. I think I dropped a minus sign because there's a minus sign here and there's a minus sign here, so that's plus. And now let's finish the rest of the equation. Minus partial I pi minus gamma 2 ci. Is everybody okay with everything that happened here? Any questions, concerns? Yes?
So if the scalar in the first equation you bring that dou of g is 0.
Oh, yes, I did. But that's a squiggle equals. That's just the principal part. I dropped the source term. The source term plus pi would be there if I wrote equals. Does that end? No, because there's only one source term. There's only one source term right here, so I could just change both of these back to equals without changing anything, because in the scalar wave, there's only the one source term. Other questions? That's a good point. I'm glad you were checking that. Okay, so let's see here. If you looked at this equation, if someone came up to you and just gave you this equation and said, can you help me simplify it? Is there anything you see here that simplifies this equation? There's sort of two things you could see if you stare at this. Yeah, these things cancel. That's one thing. And now, what is in the parentheses here? What is that? C sub I, that's just the constraint. So this is a time derivative equation for the constraint now, minus gamma 2 ci is equal to 0. So all I did is derive how this constraint will change in time. Now you can sort of see here, if this constraint starts out 0, then this equation just becomes, 0 equals 0. Or if you just plug in 0 for C, then this equation says its time derivative would also be 0. And that's what I meant by saying if it starts that C sub I, all the components of this constraint start out exactly 0, they'll stay 0, because if this term drops out, all you get is partial T of Ci is 0, so it stays a constant, right? So what you could, even with this damping term. Now, in particular, if we set this gamma 2 to 0, like if we didn't add this constraint damping term, then the problem is the time derivative of the constraint is 0 always, because this just drops out. And if that's the case, that's not great, because then if your constraint has some numerical error, maybe you have a very low resolution grid or something, and you started out with Ci being 0.1, it would stay 0.1. This constraint stays at whatever value you originally gave it. What constraint damping is all about is it's about modifying the equations so that the time derivative of the constraint changes. And this gamma 2 lets us control the time derivative of the constraint. Now, let's look at the equation like this. Partial T Ci equals gamma 2 Ci. What kind of solution do you think an equation like this has? Exponential solutions, right? So this means Ci is going to be equal to some constant, I'll call that A, E, and this is a time equation, so A e to the gamma 2t. Just guess e to the gamma 2t, and then let me try to do this right. Let me try to do this right. So we'll guess e to the, we'll just guess e to the lambda t, plug that in, and then we get lambda e to the lambda t c1, c sub I, is equal to gamma 2 c sub I. The c sub I is, oh no, I plugged that in for c sub I, so I guess there's really a vector in there, but then this would be e to the lambda t, they'd cancel. Yeah, so the lambda is just the gamma 2. So, sorry, I was just thinking in my head for a second. And so that means that Ci is going to be equal to some amplitude times e to the gamma 2 t when you actually integrate this, because it's an exponential equation. The derivative of the thing is itself, or proportional to itself. So the solution is exponentials. Now.
Yes, so I have a small question.
Sure.
So that equation del T Ci basically defines, denotes the evolution, time evolution of Ci, right?
Yeah.
So
this is an equation for the time evolution of Ci.
And Ci is the constraint equation that you have defined.
Yes, it's right here.
So can we say that since Ci is evolving with time, so that equation, constant equation, still satisfied all the time steps, like for all the time throughout the time evolution?
Yeah.
Like, because Ci is somewhat changing, right, with respect to time. That equation tells us that thing.
Yeah.
So does that mean that Ci is Ci equal to del ig minus phi I is satisfied throughout the time?
Yeah, that's the question. That's exactly the question. Is Ci going to stay satisfied as you evolve? Because here's an evolution equation for it. And the answer is it depends. If gamma 2 is 0, then the time derivative of Ci is 0 for this system. And that means that whatever size the constraint has, if it's not 0, it just remains there. It doesn't get worse, but it also doesn't get better. So in that sense, it remains satisfied to the same accuracy as before. But if you add this term gamma 2, you can change its time derivative to make it change exponentially in time. Now, did I miss a minus sign somewhere? Maybe? I don't know. Anyway, the sign of this gamma 2, the important thing is the sign of this gamma 2 will make a difference of whether this is exponential decay or exponential growth. And so by choosing the correct value of gamma 2 and with the correct sign and adding it to the equation, you can cause the time evolution of this constraint to exponentially decay instead of exponentially grow. Or instead of, in this case, staying constant if you don't do anything. So even if it starts out at 10 to the minus 1, if you choose the right sign for gamma 2, when you modify the equations, then you can end up that constraint exponentially decays with time, even if it started out big. So this is something we really do, and we do this because in GR, you don't get such a simple constraint evolution system. You find out that if you do nothing, the constraints grow exponentially, and you have to add terms like this to counteract that to cause and choose the right signs of the gammas to cause them to decay away. Okay, so that's constraint damping. It's a modification of the system that I'm mostly going to ignore in today's derivation, but you could redo the rest of the derivation for today, but you could redo all this with that extra term added. If you come over here, you've just added a term that is physically is 0, but numerically might not quite be 0. And I'm not going to do that for the rest of the day, but you could, and then you would just have extra terms here and there. Any questions about constraint damping? Yeah.
So, why we're not considering the that constraint which is not evolving in time? So, like that first solution, I mean, where gamma 2 is 0. So why we're
Okay, so I guess the question is, how did we get from this thing, which I said isn't part of the evolution system, to it's evolving in time? Is that the question? Or
no.
Okay, sorry.
That condition where gamma 2 is 0. So
Yeah.
now the constraint is now not evolving with time.
That's
So
right.
It is constant. So like, are we going to ignore this condition, or is it like that?
So it's not evolving in time. So for the rest of the derivation today, I'm just going to assume you have enough resolution that that constraint is as small as you would like it to be. Okay. Yeah. Other questions? Yes. That's right. Yeah, you choose the gamma 2, and if you choose it wrong, the constraints blow up. And I've been on the receiving end of that, where I accidentally chose it wrong and then was wondering why my constraints were growing. And it was just a silly mistake in a file somewhere. But that's exactly right. It's a thing you can tune. And there's something of an art to choosing those parameters correctly for the generalized harmonic system. For scalar wave, because it's very straightforward what it does, but there's a bunch of constraints and a bunch of constraint damping parameters in GH, and it's not obvious as clear to just know exactly how to choose them. I mean, you can figure out how to choose them, but there's also some art to it. Okay, so that was the sidebar on constraint damping. What I want to do now is set that gamma 2 to 0 from now on, and I want to start laying the groundwork to be able to tell you what we choose for this D. Remember, this D is supposed to be equal to 0 if you're at infinite resolution. Oh, sorry, yes.
Can the gamma 2 physically constrain the physical size of the object we are studying?
Can what constrain the physics? Oh, yeah.
Can it physically constrain the size of the object?
Oh, yeah, interesting question. No, this constraint damping parameter it doesn't change the physics at all, because physically in the real world, the constraint is exactly satisfied. Only numerically is it ever not 0. And so in the real world, things like the size, things you could go and measure for real, are unaffected by this change. That's why we're allowed to do it. That's what I meant by saying I'm adding 0 in a sense when I add gamma 2 times the constraint. In the real world, you're not, and not a numerical approximation of it, that constraint is exactly 0. Because that constraint is just saying, oh, you're actually solving the wave equation, or oh, you're actually solving Einstein's equations and not some other equations. Yes?
So when you take gamma 2 equal to 0, you can have enough resolution for the constraint to be satisfied.
Yeah, so I'm just going to set gamma 2 equals 0, and I'm going to assume that whatever resolution we have is enough that I don't need to care what level the constraint is. I'm just going to assume it's satisfied to arbitrary accuracy.
So my question is, if suppose you do not have enough resolution, can you choose the value of gamma so that your constraints are...
For this flat space scalar wave system, yeah. I just showed that if you choose the right sign, you can make the constraints exponentially decay, even if they start off big. Like, don't even say it's resolution. Just say, I chose the wrong initial data that doesn't satisfy that constraint for some reason. Like you can imagine choosing an initial value for G and pi and then setting phi to something wrong. And then that equation will cause those deviations from satisfying the constraint to decay away. in nonlinear equations, the constraint damping parameters have an effect, but it's not as simple. It doesn't just guarantee that you're definitely going to get all your constraints to exponentially damp away all the time. There's still things that can cause them to grow.
But will this impact when the solution of phi or phi?
Will it?
Choosing it, for example, if you do not have a solution and you choose a value of gamma that leads to the constraints decaying over time.
Yeah.
But will that impact the solution of physical behaviors?
Yeah, I mean, if you start with unphysical initial data, maybe those unphysical parts can decay away, but it's still not necessarily representing a physical system. It's just, unless you have some weird interpretation for what the constraint violation is. And that might sound ridiculous, but people have done that. There was a paper where they called it some exotic form of matter, and it was actually just the constraints weren't satisfied. But you can interpret in general relativity the constraints not being satisfied as some weird matter term. You can in the stress tensor. Interesting questions. Okay, I think yeah. Go ahead.
So do you always arrive at the equations such as like this for all the constraints?
They tend to give you things that let the constraints exponentially grow or decay. But in the full generalized harmonic system, you can't just say, oh, I'm going to set my gammas this way and never have to worry about the constraints again. You still can get into situations in practice where they're growing and because you have some kind of instability. Like one way to do that would be if you had time steps that were too big and didn't follow the Courant limit that Harold was talking about. But so you can do this in general, and you tend to get equations that are exponential in time like this, but it's not a silver bullet that stops other things that are going wrong necessarily from causing the constraints to grow. You have to actually have the gammas chosen at the correct size as well as the correct sign. Like for instance, I can make that gamma, minus 10 to the minus 15, and technically it's exponentially decaying, but that wouldn't help you in practice. Okay, nice. These are great questions, but I think I want to come back to the next thing I was going to tell you about for the scalar waves. So while I'm erasing here, let me say where this is going. What we want to do with that d alpha is choose something. We want to choose something that controls the flow of information. What we want to say with this d alpha is we want to enforce the condition that information crossing the boundary between elements. So here's an element in the logical frame. Here's its neighbor. So this is omega k, and this is, omega k plus 1 or something. And what we want is to control the information across this boundary. So here's a normal vector on this side, and here's a unit normal vector on this side, and here's a unit normal vector on this side. So we're going to call this the exterior side and this the interior side. And yesterday, there was some question about, well, how can these normal vectors be different? They're both unit vectors. I totally get that, and I was confused about that too. So let me try to explain a little bit why I have two separate normals. They're both pointing in the same direction. For simplicity, let's just call that the x direction. These elements happen to be aligned so that they're right along the x direction, right? Well, then how would you make a normal vector across the elements? Well, what you would do is you would say, let's just make some vector that points in the x direction. And so I'll say I'll just start out with a vector like x hat that points in the x direction. But in curved spacetime, maybe instead of writing it as x hat, I'll just write it as 1, 0, 0, where these are the x, y, and z components. But in curved spacetime, this is not necessarily a unit normal vector. It's in the right direction, but who knows what its magnitude is. So let's just call this vector vi or something, right? So you picked a vector in the right direction, but now you have to normalize it in order to make it a unit vector. So you have to do v. If I wrote it as a vector, it would be v dot v. You have to do that and then square root it and then divide your original thing by that. And the key is this dot product, if you're in curved spacetime, is going to end up being gamma ij, well, that's the spatial metric, vi vj. So there's this spatial metric that enters into it. And the issue is, in discontinuous Galerkin, you are the spacetime metric and therefore the spatial metric that's one of your variables, your U alphas in the DG formulation, those are allowed to be discontinuous across the boundary as long as those discontinuities converge away. And that means that this factor that goes into normalizing your vector is different on either side. And as a result, the numerical X, Y, and Z components of your normal vector are different on either side of the boundary. It's because of the normalization. So I just wanted to try to clarify that. So what I want to talk about now is, I said we want the information that leaves the neighbor and enters the element to be minus the information that leaves the element and enters the neighbor, some kind of conservation of information. But I haven't defined what I mean by information. So that's what I want to talk about now. What controls the information flow? Or what controls, another way to put it is, what is flowing around that would need a boundary condition? What we're really talking about is, what do we want to do for the interior boundary conditions? And when you've got a system like this, then the thing that controls the flow of information for the non-conservative terms, like in scalar waves, are called the characteristic fields and characteristic speeds. Now let me simplify for the rest of today. For the rest of today, I'm going to assume vacuum. So this term is 0, and this term is 0, and this term is 0. All the fluxes are 0. We're just doing equations like generalized harmonic or scalar wave. Neither one has any flux terms. So the only internal boundary condition we have to worry about is this d alpha. And d breve j alpha times phi j, sum over those, that's what I mean by just d alpha. So I want to start building. I don't think I'll get there because we took a little detour into constraint damping. We'll get there tomorrow. But I want to start laying the groundwork for how to explain the last piece of the DG recipe. What is this d alpha if you're doing binary black holes? Okay. So let's talk about what are characteristic fields and characteristic speeds. These things, they are a combination of the variables we're evolving that describe how information is flowing around. Information in the sense of you need a boundary condition. It tells you when you need boundary conditions. So I'll make that more precise in a little while. So I'm just going to say characteristic fields and speeds. All right. So what you could imagine doing is looking at the principal part of your equations. Look at the principal part of your equations and then try to look for some wave solutions. And maybe look for some high frequency wave solutions. Harold's going to make this more precise tomorrow. And if you do that, you can then try to get a combination of your variables, g, pi, and phi I here, that correspond to a wave in some sense. And that's what I sort of mean by the flow of information. And I'm not going to drive this any more than to sort of wave my hands like that, but that ends up leading to the definition of characteristic fields and speeds that I want to show you. So let me pull up my notes here. And now I'm back to characteristic speeds. So we've got this general system of equations that has no fluxes, but otherwise it's this generic form of evolution equations we've been talking about. And the principal part, in fact, is very simple because there's no source term either. It's just partial T U alpha plus B I alpha beta, and here are the spatial derivatives, partial I U beta. And if this is the principal part and you're ignoring the source terms, that's it. That's what you have. Now, it turns out that if you want to know about flow of, well, not necessarily physical waves, but of the waves carrying information such that that's what you care about for boundary conditions, it turns out that the combination of the fields that matters for that, the characteristic fields and speeds, can be found from these matrices here. Remember, these are 3 matrices that we wrote down when we were explicitly for the scalar wave system, and Harold wrote them again this morning. And how exactly does that work? Well, it turns out that, well, think of it this way. This is three matrices, and you can think of each matrix, B alpha beta X, B alpha beta Y, and B alpha zeta Z. You can think of those as three components of a vector of matrices, one component for each direction. The component of B that matters when you have a boundary is the component normal to that boundary, because that's the direction that you care about, flow across the boundary, perpendicular to it. So this whole formalism is based on Ni Bi alpha beta. So by dotting the normal vector into Bi alpha beta, and because I'm doing this for the flat space scalar wave, in the end I won't have to worry about up and down indices, but here I've written them like this in case there's a metric that raises and lowers them. This thing is the normal component of this vector of matrices, the component that's in the direction either outgoing or ingoing perpendicular to that boundary. And if you want to find the combination of variables that describes information flow across that boundary, then what you end up doing is an eigenvalue problem. It's a left eigenvector eigenvalue problem. So what you do is you say, here's an eigenvector, and there's a bunch of them. I'm going to label which eigenvector we have with alpha hat, and alpha, the actual alpha labels the index in terms of the different variables that you have in this matrix, the different components of this matrix that you have. So this will be a column vector in alpha, and multiply that by Ni Bi alpha beta. And if this is an eigenvector, then left multiplying this row matrix by this matrix isn't going to change anything. It's just going to give you an eigenvalue. And sometimes those are called lambda, but because they turn out to be speeds, I'm going to call them each eigenvector, which I'm indexing by alpha, is going to have a corresponding speed. And then that vector hasn't changed. So you can think of this matrix. This is one for the flat space scalar wave. It was a 5 by 5 matrix when we looked at it before. So you can think of this matrix, and then you could say, well, what are the eigenvectors that when I multiply them by that matrix, I just get the vector back rescaled, but not changed in direction. So solving this problem, then if you solve this problem, then the characteristic fields are a combination of the variables. They turn out to be W alpha hat, there's one per eigenvector, and that's equal to the eigenvector alpha times U alpha. Remember, alpha tells you which variable you have, G or pi or phi X or phi Y or phi Z. And so each eigenvector is going to be some combination, some linear combination of those variables. Those are going to be the fields that you care about. Those are the fields that you would have to set boundary conditions on if the flow is into the domain. And that brings us to the characteristic speeds. The characteristic speeds are just the alpha. The speeds will, the way I've drawn the normal vector here, the speeds will be positive if the information is, or the wave represented by the combination of the variables is flowing out of the element and into its neighbor, because I've chosen that to be the positive normal direction. These speeds, these eigenvalues will be negative for flow into the element. So that's the definition of characteristic speeds and fields. And what we put into this D alpha is a function of the characteristic fields and the characteristic speeds. Yes?
Why are you not considering the del Iyer?
Oh, why did I cross these terms out? Especially this one? Yeah, good question. So this term shows up when you have equations in flux balanced form. This term is very important for correctly handling shocks or sharp features. So when you have matter in your simulation, then this term shows up. I'm focusing my attention for now and for the rest of the week on the binary black hole problem, which is vacuum. And we're not putting an accretion disk or anything around it. It's just two black holes, curved spacetime, and nothing else. And in that case, in curved spacetime, there are no sharp features. There are no shocks. So there's no need to try to write the equations in this form. And it turns out in both of these formulations, there are no terms like this for both generalized harmonic and scalar wave. So I'm just doing a particular subset of DG for those systems of equations that don't have flux terms in them. So that's why I'm ignoring them. I'm just only talking about certain systems of equations now, the kind you care about for binary black holes or the scalar wave.
But doesn't that have information flowing from one element to the other?
Yes, and you control that with the G. So the D is the boundary correction term for the non-conservative terms. If you don't have B's, if these B's are all zero, like they are in hydrodynamics equations, then you wouldn't have this D, that'd be 0, 2. Similarly, if your equations happen to not have these fluxes, then these G's don't show up. So it's just a matter of choice. The equations for magnetohydrodynamics, usually you want to write them in a form where all of them have fluxes, but they have no non-conservative terms. And in that case, you wouldn't have a D, you would just have a G. And if you're just doing vacuum GR, you'll have the non-conservative terms, but you won't have the flux terms because the generalized harmonic system just doesn't have these terms. And you don't need them because the main reason you would want to have these instead of these is to handle sharp features. And in GR, that's not necessary because everything's smooth. And then if you try to put GR and MHD together, then maybe you have this combination system where you have both. Other questions? Yes. Yeah, like where did this come from? I'm going to defer that to Harold to derive tomorrow. It turns out that if you look for high frequency wave solutions that can get you a feel for an equation kind of like this, and that's sort of suggestive intuitive motivation, but I have not derived it. I'm just saying that's what it is. And I'm going to let Harold derive it tomorrow. Okay, so what I want to do for the rest of the time is show you a specific concrete example of how this actually works. For the scalar wave system with gamma 2, 0, I want to show you how do you actually find these characteristic fields and speeds. So you're going to have to solve, well, we'll see how far we get today. So you're going to have to solve the scalar wave system. Now, originally, when we weren't talking about boundaries with some normal and I, we thought of these B's as three separate matrices, Bx, By, and Bz. But once you introduce a boundary, there's one direction that's more important than the others in some sense, the normal direction. And that turns out to be true for the system of equations itself, for the variables too. So what I'm going to want to do is sort of take the same system of equations, the equations for G, pi, and phi, but think of, instead of X, Y, and Z components, think of three different components. And let me show you what I mean by that. So U alpha, originally we chose our variables to be G, pi, and phi X, phi Y, and phi Z. What I'd like to do instead is instead of thinking of this vector phi I as three components X, Y, and Z, let's think of it as a component normal to the surface and then two components tangent to the boundary. So you would have a normal component pointing this way, which I called the X direction here, but it's not necessarily the X direction in general, it's just the normal direction. And then you have two components that are tangent to the boundary. Sorry, is there a question? Okay. So what I want to do instead is think of the variables as G, pi, phi, what do I want to call this? I want to call this phi perpendicular, and then the two components of phi that are parallel. So in general, there's one component that'll be perpendicular to the surface, and then that leaves two more to define however you want that are tangent to it. So I want to think of this, the set of variables we have like this instead. So let's think how we can rewrite phi I in terms of a component normal to the boundary, and then a component perpendicular to the boundary. So if you want to find the component of phi sub I that's normal to the boundary, what would you do? Yeah, you would dot it with the normal vector. And I'm going to freely raise and lower indices because this is flat space now. So you would just do that. And so what I mean by phi perpendicular is really just, I'm going to use L for the summation index here, just because so I don't conflict it with other indices later. So this is just some dummy index I'm summing over L. That's the dot product. Now, the trickier question is, what is this phi parallel? How do you get the components that are perpendicular? Yeah, basically what you need to do is you need to start out with phi I and then remove the normal component. And let me show you how that works, and then I'll prove that that's correct. So let's start out with phi sub j, let's say. And now I'm going to multiply that by something here, delta, let's say delta jk minus nk nj. This is called a projection operator. So when you first look at this, maybe it's not clear that this does what you want, right? So what we're looking for are the tangential components. So for the tangential components, if I were to take phi parallel j and dot that into the normal vector, what should I get? 0, because they're tangent. Exactly. So let's see if that's the case here. Let's take this whole thing here. This whole thing you could call aspirationally, we could call that phi parallel sub k. And then let's check if that's actually satisfies this by multiplying and summing with an nj. So then this would become phi j times delta jk minus, delta jk nj minus nk nj nj. Now, what is nj mj summing over j if it's a unit vector? Well, it's a spatial vector, so it's actually just going to be positive 1. What? Sorry. Oh, I already summed over j. Sorry. I mixed up the j's and k's, didn't I? Is that better? So now I'm going to take phi k, and that's contracted here and here, and then here's the j summation. Yeah, okay, so now it bounces. Sorry about that. Are there any questions? Okay. So now let's check if this is true. nj, nj, it's a unit vector, so that's just 1. So this is equal to phi k times, this term is just going to be nk, because nj, nj is 1. But then if you contract nj with this Kronecker delta, what is that going to be? Yeah, that's also going to be nk. So sure enough, this is the parallel component. So from now on, I'm going to write this component as phi parallel j, and we'll just understand that this includes both of the tangent components. And these are the variables that I want to find a combination of that gives us the characteristic fields and the characteristic speeds. And we'll just remember that phi j parallel is defined in terms of this operator here. Okay, so let's get rid of that. And I don't think we need this anymore either, but we'll just write phi j parallel equals phi k delta j k minus nj nk. Now, what we have to do is, oh, sure.
I'm a bit confused about the fact that phi j is supposed to be a two-component vector, right?
Yeah, well, it has 2 independent components. I've written it as phi j, but it's definitely pointing somewhere in the plane perpendicular to the normal. So you know, if you have a vector in a plane, you're still free to write it with 3 components. It's just one of the components is 0. I just haven't said which one. So it's a great question. You're saying this index could take one of 3 values, but I just said this thing is in a plane, so it really only has 2 independent components. And those can both be true. It's just if you turn your coordinates so that one of the axes points along the normal vector like I did here, then one of them will be 0. But you could instead imagine choosing coordinates so that your axes were rotated in some way so that the thing that's tangent actually has 3 non-zero x, y, z components. X, y, and z don't have to point in the normal direction necessarily. This still is the same amount of independent components, but if in terms of x, y, z, that j might take any of those values. Interesting question, interesting point, that's true. Okay, so what you could imagine doing next is trying to figure out what the principal part of the scalar wave equation is in terms of all these variables. Now, because time is running a little bit short, I'm not going to actually derive it, but I can show you how it turns out. What you would have to do to derive it is you would do things like rewrite this phi k in terms of its normal part and its perpendicular part, and then plug that in for phi k everywhere. So in particular, you can always write phi I is equal to, you can always write phi I is equal to, you can always write that that's equal to the normal part, which is phi L n L times the normal vector, plus the perpendicular part, or the parallel part, phi parallel j, phi parallel I. So everywhere you have a phi I in the other equation, you replace it by expand it into its normal part plus its tangent part. And then if you expand all the equations out, you'll end up finding a system that looks like this. Partial Tg is the principal part of that equation remains 0. Partial T pi plus nk partial k phi L n L plus partial k phi parallel k. That principal part is 0. And then you'll have an equation for the normal part, partial t of phi L n L, and that ends up just being plus nk grad k pi. And then the last one is partial t phi parallel j, and that ends up being plus delta jk minus nk n j partial k pi. So if you look at this, now there's an evolution equation for g, for pi, for the parallel component of phi, and for the tangential components of phi. And you get it, I'm not going to do it now, but you get it by taking this and plugging it into those equations over there. There's one little trickiness when you do that. If you're dealing with the principal part, you are allowed to move these normal vectors through the partial derivatives, even though the normal vectors might depend on space, depend on where you are. And the reason for that is, if you imagine doing a product rule here, like think about this term right here. If you did a product rule, the first term would involve a derivative of phi, the second term wouldn't, and so then it wouldn't be part of the principal part anymore. And if so, that's why if it's principal part, you can move derivatives, the ends through the derivatives. And that gives you this form of the equations. Now that you have a set of equations with derivatives of pi here, and derivatives of phi, you can come back to the general form of the equations and figure out what the b's are. And in particular, for our purposes, the only one we really need is bi. We only need the normal component of bi alpha beta. So we just need one matrix. And if I'm not going to do it, but if you were to read off coefficients from here, like for instance, the coefficient in the pi equation, I'll just do one of them. If you look at the pi equation, the coefficient of the gradient of the normal component of phi is just nk, for instance. So if you were to try to write, this whole thing down, then what you end up getting for that one matrix ends up looking like this. You end up getting 0, 0, 0, 0, 0, 0, 1, and j, 0, 1, 0, 0, 0, 0, 0, 0. So we've taken the normal component of B, so there's no more spatial index there, but the reason there's a j here is because this B is multiplied by the derivatives of your variables. And what that vector looks like, if you were to take this bi and then multiply it times partial I u beta, with our variable choice here, that would be partial IG, partial I pi, partial I, oh, I shouldn't use I because I already summed over it to take the normal component. So I guess this would just be the, end up being multiplied by a normal derivative or something. But anyway, partial, the normal component, and then partial phi parallel k. So because this phi, or j, because this phi, this variable here has a j in it, everything that's going to, when you multiply these together, everything that touches this last component has to have a j on it as well. So you end up getting a scalar out at the end. Anyway, I don't know if that helped, but the point is this normal component of the b's ends up being a matrix where most of the terms are 0. One of them is your normal vector and the other non-zero ones are just ones. This is a matrix. You can find the eigenvectors and eigenvalues of it in the usual way. You just, subtract the eigenvalues down the diagonal, take the determinant, solve for the roots. You've got the eigenvalues, then plug them in, and you get the eigenvectors. Now, if I had more than 10 minutes, I might actually work through that math for you, but since time is short, I'll just tell you how that comes out. If you were to solve that matrix for its eigenvectors and eigenvalues, then, well, maybe we can at least start with the solution. So you start out to get the eigenvalues. The determinant would look something like minus v alpha hat, minus v alpha hat, minus v alpha hat, minus v alpha hat. And then what are the other non-zero terms? There's a 1 here and a 1 there. And then everything else is 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And that determinant has to be equal to 0 for this, for the eigenvalue equation to have a solution. Bring this to the other side, and then to get a homogeneous solution, you end up with that. This is just the usual eigenvalue problem. If you were to solve this, you can think of this as, well, 2 of these rows only have 1 non-zero term. So ultimately, this determinant is going to be equal to v alpha hat squared times the determinant of this 2 by 2 matrix in the middle, which is v alpha hat squared minus 1. And that means the eigenvalues, there's 2 eigenvalues that are 0, and then this thing has solutions plus and minus 1. So the possible solutions for the eigenvalues are 0, plus 1, and minus 1. And those are the 4 different characteristic speeds corresponding to the scalar wave system. And you find it just by taking the normal component of the b's and then finding the eigenvalues of that matrix. What happened to what? NJ. What happened to it was, nothing happened to it, but it doesn't survive the determinant, because if you take this determinant, start at the top row, this is the only non-zero term, so then you just take the determinant of this 3 by 3 matrix, when you take the determinant of this 3 by 3 matrix, this is the only non-zero term. And so then you only take this 2 by 2 determinant. And so the NJ is there, but it doesn't survive because of all the zeros. So that's how you find that there are 4 different combinations of the variables. Those are the eigenvectors. And 2 of them have speeds of 0. They don't correspond to any flow across the boundary. One of them has a positive flow, which corresponds to outgoing motion, and one of them has negative flow, which corresponds to ingoing motion. If you want to know what combination of the fields are carrying the information, all you have to do is take these eigenvalues, plug them back into this eigenvector equation, and find the answer. And it turns out it's just some algebra if you do that. And it turns out that you end up getting the following. You end up getting there's 4 different eigenvalues, so there's 4 different possible eigenvectors. So the different eigenvectors turn out to be 1, 0, 0, 0, 0, 0, 0, 1. And then the last 2 eigenvalues end up being, eigenvectors end up being 0, 1, plus or minus 1, plus or minus nj. So the nj does survive in the eigenvectors, just not the eigenvalues. So these are 4 different eigenvectors because one of them uses the plus and one of them uses the minus. And then the characteristic fields are just these eigenvectors dotted into U alpha. And U alpha is just written right here. So when I see 1, 0, 0, 0, that means one of the characteristic fields is just G. So this one has a characteristic field that turns out to be G. This one has a characteristic field that turns out to be phi parallel J, which is defined, I've saved the definition over here. It's phi k dotted into this projection matrix, delta jk minus nj nk. And then the last one's down here. Well, the second component is pi, and so this eigenvector, I need more space. I need to erase something. The last eigenvector, I'll write it above it, is going to be called, well, let's see. So this is one eigenvector, this is one eigenvector, and then this one is going to be pi plus or minus the normal component, and L phi L. And then it ends up being plus or minus nj times phi parallel j, but guess what? Phi parallel j is orthogonal to the normal vector, so that term doesn't survive. And it ends up that this, and this are the characteristic fields. So these are combinations of your initial variables. 2 of them are just some of the variables themselves. But then this one is a combination of pi and the normal component. And it turns out that these are the ones that have speeds minus 1, and these are the ones that have speed 0. So if you want to set a boundary condition between elements for the wave equation, the thing that you need to care about are the plus or minus 1s. Like suppose this element were on the edge of your domain and you really needed to set a boundary condition there. Then the boundary condition that you would have to set on your differential equations ends up only involving the one of these with a minus characteristic speed. So the only combination of the variables that you would have to control on this on the boundary would be, well, let's say if you had this element here and there was no neighbor and this was the outside and you cared about what do you have to set a boundary condition on? Only the combination that has a negative characteristic speed, which turns out to be pi minus the normal component of phi. And so, and that turns out to have a speed of 1 in my units because I set the speed to be 1, but that could be the speed of light or whatever for the waves. And then that corresponds to information flowing in. So that's what I meant by, that's a bit of an example of what I meant by characteristic fields and characteristic speeds. You can always find them. You could find them for the generalized harmonic system, just they're more complicated. And they're the combinations of variables that have to do with what's flowing back and forth and with what combinations do you need to actually choose to have the system, the evolution be well posed. And the combination you have to choose is the combination that corresponds to characteristic fields whose speeds are flowing in from the outside. Next time, I can finish the discussion by showing you how we use the characteristic fields and speeds to choose what this d alpha is, and then that concludes what I wanted to tell you about dg. And I should have some time after that to show you a little bit of stuff on the computer about some specific domains that we use, that we construct out of these hexahedral meshes, and some updates, like some examples of actually doing this for some binary black hole calculations. So thank you very much for participating today, and I'd be happy to answer any other questions you might have. Okay, yes.
What do you mean by well posed?
Oh, well posed. I threw that in there at the end. Well posed means that initial data, the same initial data has a unique solution. If equations aren't well posed, then the same initial data can give you different answers depending on numerical circumstances. Like just different round-off error, for instance, could give you different solutions if you're not well posed. So if you're doing a time evolution, in order to not get different solutions for the same initial data, which is a way to say numerical garbage, in order for that to happen, you must impose boundary conditions on those characteristic fields on the outer boundary that have negative speeds or incoming speeds. In other words, you're controlling what's coming into your grid, not what's going out of your grid. Other questions?
For any PD system, you have to define this P.
Yeah, anytime you have a boundary between two elements that gives you a normal vector, you can construct the normal component of this B matrix, and from there you can construct the characteristic fields and the characteristic speeds.
And all of this has to be done analytically before you.
Yeah, usually, yeah, like for generalized harmonic, we figure these out analytically and then code them up, just like for scalar wave. Because these are the things that you actually have to measure and control for the boundaries. All right, well, I'm happy to answer any other questions afterwards, but thanks again for participating, and I don't want to keep you from lunch anymore.